Okay, so we can continue from where we left last time. So turn off your microphone, turn on your microphone when you have to ask questions. Attend tutorials to practice more problems. So today we will actually do problems. So consider the PDF of a random variable x, and this is the PDF. The question is find the constant c, okay, and find the expectation of x and variance of x and probability that x greater than or equal to 2. So these are the solved examples that I will go through just for quick practice. So to find c, what we will do is we know that if we integrate the PDF from -infinity to infinity, it should turn out to be 1. So that's what we are going to use, and then we integrate. Okay, but we know that the range of x is between -1 and 1. Is -1 and 1, right? So the integration -infinity to infinity will boil down to -1 and 1, and then this is the PDF. And then if you solve this integration, then and here you have 1 here, right? So if you solve for c, then you get c equals to 3/2. So it's very simple. Expectation of x we know is UFU, okay, or XFX, whatever you feel like. So here now we have to integrate this. So if you do u and then fxu, then that will be u cube. Okay, and again the range of integration is -1 and 1, because this is the range of your PDF where it's valid to define. Otherwise it's 0 anyway. Okay, so this is how you have the limits of the integration, and then if you do the integration, it turns out to be 0. So here it turns out to be 0 because this integral is 0. Okay, and this integral is 0 because it's an odd function, right? So odd functions are symmetric about the origin. So odd functions are always symmetric about the origin. Okay, so the area under this will be the area under negative of the area under this, and they will get cancelled. Okay, so that's why this u cube is an odd function. Is a odd function, that is g of minus u is minus g of u. Okay, so for odd function they are symmetric about the origin. Okay, so hence the integration cancels out. Okay, if the range of integration is symmetric about the origin also, then the integration cancels out. So this is like a positive area and this is like negative area. And we have variance of x is given by expectation of x square minus expectation of x whole squared. So this will be, but expectation of x whole square turned out to be expectation of x 0, so that term goes to 0. So we are only left with u square fx this, and then if you integrate, you get this. And probability that x greater than or equal to 2 again can be found using PDF. So it's just that we have to integrate it from the correct range, right? So this was so x is greater than or equal to half, so it's like half to infinity. Okay, by definition this half to infinity, and then this is the PDF of x. Okay, so this is like PDF of x. Okay, so if we put in the values, so we know that the range of x is up to 1. Okay, so that's why it became 1 from infinity, and then the PDF of x was c times x square, but c was 3/2. So if we put in all the values, then we get 7/16. So that's how we compute the probability. And let us consider another PDF. So this is the PDF of a random variable x, and this is defined over all of R. So one thing to check is that fx x will be so -infinity to infinity. In this case, the range is all of R, so this must turn out to be 1 for this to be a valid PDF, and it will turn out to be 1. Okay, so if y is x squared, then find the CDF of y. So in this case, we are told to find CDF of y, which is a function of x. Okay, so in this case, we observe that the range of y is 0 to infinity. Okay, so range of, because y is x squared, range of x is -infinity to infinity. Okay, but since y is x square, so the range will become 0 to infinity. And for y in 0 to infinity, we can write like this. So so the PDF is fyy is probability that y less than equal to y is same as probability that x square is less than y, and x is minus y square root y to square root y. So this becomes the integration from minus square root y to square root of y. We integrate the PDF. And again, one more thing we are using from calculus. Recall calculus, in particular the integration properties. So this, if you can observe, this is this an even function or odd function? So is this even or odd? Even or odd? Okay, so what do you think? Is this an even or odd function? Can you tell me in the chat if this is even or odd function? Even. Okay, Akshat, even, Mehul even, Shivam even, Lukesh, Sarah, yeah, all even. Okay, yeah, it's even actually. So yeah, that's correct. So it is even because for even function, remember g of minus u must be just g of u. Now what is the properties of, what is the property of even function? So I said for odd function, for odd, it's symmetric about origin, right? About origin. Now what about even? Can you have something similar for even? It is symmetric about what? For even function is symmetric about? Tell me in the chat. Y-axis, exactly. Prince is correct. So the even function symmetric about y-axis. Symmetric about y-axis. Okay. So symmetric about y-axis would look like something like this. So for instance, let us say just mod function if you take, then it's a even function because g of minus u is g of u. Okay, so this is like mod x, mod u. Okay, so g of u is mod u. And this is the y-axis. So this is symmetric about y-axis, right? So it's the same thing like here. It's like you put a mirror and then you have a mirror reflection on the other side. Okay. So what will be the consequence of integrating a symmetric function? So let us see this example here. So if I have to integrate this like this, and let us say I have to integrate from minus a to a. Okay. So integration minus a to a of a symmetric function g du u. Can you simplify this further? Like what can I do, right? So I have to area under this. Okay, so from here to here I have to do. So I have to compute the total area this, right? So I have to compute total area this. So can I like simplify the integrations? Now the integration is from minus a to a. So what can I do? Can I use the symmetry, right? So that's the question here. So can I use the symmetry? Because this this area is going to be the same because the function is symmetric about the origin. So function symmetric, not origin, but about y-axis. Y-axis. This implies area is also symmetric about y-axis. The area under curve, in this case it's the mod x curve, is also symmetric about y-axis. About y-axis. Okay, so this is symmetric in the sense like it's same. So we can simplify this, right? So we can write instead 0 to a and then twice the area. So it's like twice the area 0 to a and g of u du. So that's the simplification we can do. Okay, if g is even. Okay, so that's the property we have used here. Okay, so this is like minus a to a and this is a even function. Okay, so we have written two times the integrand. Okay, and then we have changed the limits from 0 to square root 2. And then if we integrate, square root y, and if we integrate this, then we will get something in terms of y. So that's the PDF. Now, so to summarize, we always like to summarize what is the PDF. So PDF is like 1 minus e to the minus square root of y for y greater than equal to 0. That's the range of y we have found. So that means y greater than equal to 0. And otherwise, that is y less than 0, it is defined to be 0. So that's the CDF. Now consider another problem, the PDF of the continuous random variable. So it's given here, and we are supposed to find the probability that x is less than equal to 2 by 3, given that, so this is the conditional, and x greater than 1 by 3. Okay, given that x greater than 1 by 3. So this is the formula we know, right? So probably that x less than equal to 2 by 3, given that x greater than 1 by 3, we invoke the joint, the joint, right? So so we do intersection. Okay, so intersection of this x less than equal to 2 by 3 and x greater than 1 by 3 is this. Okay, so this is the intersection. So if we do that, and then we divide by the probability that x is by probability of b, right? So which is probability that x greater than 1 over 3. So if we do the usual stuff, now this is the probability we are supposed to find. So this will become the limits of the integration. And then we have the PDF, which is the 4x cube. And then we divide by the limits of integration will now be starting from 1 over 3. And it stops at 1 because the range of x, if you see, upper limit is 1. So no point in integrating beyond that because that will be 0 anyway. So you stop at 1 here. And then you integrate this, and if you could do these calculations, then you will get this answer. Okay, so this is just the practice of. Okay, let us consider problem 4. Consider the PDF of random variable x. So this is the PDF. Whether it's a valid PDF, check for validity. Check for validity. Okay, so in other words, fx x, it should always satisfy this. Any PDF should satisfy this. So check for validity, and imagine that y is a function of x, in this case 2 by x plus 3. Now the question is find the variance. Okay, so what is the property that we are looking at to use here? So it's like a times x plus b, something like this, we know, right? So this is of this form. So this is like a square variance of x. Because shifting the data by some constant, where a and b are constant here, it doesn't change the spread of the data. In other words, it doesn't change the variance. So this is something we can apply here. So variance of this will be like this guy will go away. Like constant translation of the random variable doesn't change the variance. So now we are left with this variance of 1 over x. Okay, so how do we compute the variance of 1 over x? The variance of 1 over x, we apply the usual definition, which is expectation of 1 by x square minus expectation of x whole square. So now expectation of 1 over x is this. Okay, so you can check the PDF, and then so it will turn out to be this, and expectation of 1 by x square will be this after integration. So it's a simple integration, and hence the variance of 1 over x will be given by so variance of 1 over x will be computed from this. So this from here, variance of 1 over x square is 5 by 2 minus 17 by 12 whole square. Okay, so if you do this, then you get this. And hence variance of y now will be computed from here, which is 4 times the variance of 1 over x, which is 71 over 36. Okay. Okay, so now let us see problem 5. Problem 5 says that x is a uniform distribution with parameter a minus pi by 2 and parameter b is pi, and y is sine of x. Now find the PDF of y. Okay, so this is one of those problems where we would like to invoke method of transformation. Okay, so that's something we method of transform, right? So that's something we saw in the last class also, but this is the case where, yeah, I mean, this is one of the cases where it's not strictly monotonic. Okay, so if we use method of transform, so what were the conditions that we were requiring? So it should be like continuous and differentiable. So continuous and differentiable. Okay, and another thing that we needed was like there were many cases, right? So either g is increasing or decreasing, or if the general case is like g is piecewise increasing or decreasing. Okay, by piecewise I mean on some intervals it's increasing. The interval can be partitioned such that in some interval it's increasing and in some interval it's decreasing. Okay, so that there is something we are looking for, like we recall this method of transform, and then we had this formula that we can use from method of transform, right? So let us see what are the things we have. Like first thing is like continuity and differentiability is given because sine is well known to be differentiable, and we also know what is the differentiation of sine x, which is cos x. So it is continuous differentiable, but it is not strictly increasing or decreasing on the given interval, which is minus pi by 2 to pi. So it will increase from minus pi by 2 to pi, and then it will increase from 0 to pi by 2, and then it will decrease from pi by 2 to pi. So it's like there are three pieces here. So let us so this G is differentiable, that's we noted down. G is monotone, not monotone actually, but it can be divided into a finite number of regions in which it is monotone. We observe that the range of x is minus pi by 2 to pi, so this is taken from here. And we observe that the range of y is minus pi to pi. So you apply sine on this interval, and then you get the range. So the lower limit will be -1 and upper range will be 1. So so what are the observations we have in this case? Like we need to plot and see how we can divide this into finite number of regions. So for sine x, we are going to plot the sine x, right? And then from there we will see what is the so sine x. So let us say this is like pi by 2, and this is pi, and this is like 3 pi by 2, and this is 0, and this is minus pi by 2, and this is minus pi, minus 3 pi by 2. Okay, so the sine curve will go like this. Okay, and then it comes back, and then it goes like this, right? So let us say it's 2 pi. Okay, so the problem is defined over minus pi by 2 and pi. So our focus is starting from here, minus pi by 2 to pi. Okay, so this is the focus, and what we see is like minus pi by 2 to 0, it's increasing. So the partitions of the region, right? So the partition is, so we see the partition of Rx as follows. So we see this as minus pi by 2 to 0. Okay, so this is our first partition, and 0 to pi by 2, and then pi by 2 to pi. Okay, and how we are doing this? We are doing this by looking at where it's monotonic. So here from pi by 2, minus pi by 2 to 0, it's monotonically decreasing. And then from 0 to pi by 2, it's monotonically increasing, and then like somewhere here, and then after this pi by 2 to pi, it's monotonically decreasing. Okay, so here it's like increasing, here it's like decreasing, here sorry, here it's like also increasing, and here it's like decreasing. Okay, so we have partitioned our domain into three parts where the function is monotone. Now using a method, we will use method of transformation. So in method of transformation, the steps involved where we have to find inverse function locally, like piecewise inverses we have to find. So from here to here, we can find the inverse function of this curve. Okay, from here to here, we can find the inverse of this function. Okay, from here to here, we can find inverse of this. Okay, so the reason why we have to do this, this partition is to have a unique inverse. Okay, that's the whole idea. So I mean, okay, I don't know why I took this interval, right? Like I don't need it, right? So I mean, it's from here to here, it's monotonic anyway, right? So I don't see why I should split this. So I should take like minus pi by pi by 2 to pi, I guess. That will be okay. Yeah, because that's monotone from minus pi by 2 to pi. So I will combine this actually. Okay, and then from here it's decreasing. Okay, so let us combine this. You take a union of this. So actual partition would be minus pi by 2 to pi by 2, where it is increasing, and then union of pi by 2 to pi. Okay, let us do this. Okay, so since this is monotonic here, like inverse is guaranteed. Okay, but if you go from let us say here to here, the inverse is not guaranteed because it is no longer like 1 1. Okay, it is on 2, but it's no longer 1 1. So that's the problem here. Okay, for two different x, I get the same height y. So it's not 1 1, so it's not invertible from here to here. So it's because of the invertibility that we need to partition, so that inverse is well defined. Okay, so with these things in mind, now we can go ahead and now work out the details of these, right? So what we need is we want to find the PDF of the function of the random variable. Okay, so in other words, PDF of y. So we are given that y is some function of x. Okay, in this case it's like sine of x. So g is differentiable. Okay, and g is not monotone. So what are the things we have observed? So we have observed is that the range of x is minus pi by 2 to pi, and the range of y is minus 1 to 1. Okay, now so now, yeah, so we have the partitions defined and we have the ranges well defined. So what we have to do is now, so what will be the partition of the ranges, right? So ranges in this case, right? So of the y, I mean. So we have partitioned the range of x, but what are the partition for the ranges of y also, like for so it's like minus 1 to 0, and then 0 to 1 are the partitions for y actually, right? So so yeah, minus 1 to 0 is 1, and then 0 to 1. Yeah, from 0 to 1. Yeah, 0 to 1 will include both the curve here. Yes, and okay. Yeah, so let us now write down the piecewise piecewise terms that we get from the method of transform, right? So if this is fy y, okay, so this is fx x1, okay, and this is like mod of g inverse x1, okay. So x1, so here x1 is like y is yeah, sine of x1, okay. This is what we are talking about here. So for so this will be f of fx of x1. X1 is sine inverse y. So this is fx, x1 is sine inverse y, and divided by g prime of x1, right? So if we, so this is the g of, we also see this as g of x1, okay? So if I differentiate this with respect to x1, then I get a cos of x1, but x1 is sine inverse of y. Okay, now this is so sine inverse of y, right? So sine inverse of y is how much? Okay, so sine, and fx is a uniform distribution, remember? Fx is a uniform distribution, and sine inverse y in so we have to look at the range of sine inverse y. Okay, so let us say that I'm looking into y in 0 and 1. Okay, yeah, or y in -1 and 0 range. Okay, so let us say I restrict my y for the moment to -1 and 0 range. So this is uniform. So fx will be uniform. We are looking for uniform over -1 and 0. Okay, so this is like fx of the random variable with the limits -1 and 0. Okay, so this is like the PDF of the random variable which takes value between -1 and 0. So uniform -1, 0. Okay, so this boils down to this. So, and yeah, so this is like so sine inverse of y, which is, okay, I think I have done something wrong here. So this is like, yeah, so let me do it another way. Fx of sine inverse of y, which is in the range -1 to 0, right? So -1 to 0. Okay, so what will be this? But sine inverse from -1 to 0, right? Let us see the picture here. So -1 to 0, I have split in this form. So -1 and 0, and so -1 and 0, this will boil down to x being in -π/2 to 0, right? Okay, so -π/2 to 0, right? Yeah, so sine inverse y, if I restrict my y to -1 and 0, then -1 to 0, or let's see. So you do -1 to 0, and if you do sine inverse of that, then the range that we will get will be the range of x we will get will be 0 and -π/2, like -π/2 to 0, right? So that will there is something missing here, whether something there in the question, I guess. So if we go by -π/2 to this, yeah, they say this is uniform, then the range of sine inverse y will be -π/2 to 0, actually, right? So if it is -π/2 to 0, then what I will get is π/2. So it's okay. So let us go ahead with, I think. So within -1 and 0, this will be around. So sine inverse y will be around like -π/2 to 0 x range. So this will be uniform, like yeah, over this, right? So this will be like 0 minus pi by 2. So it will be like pi by 2 here. Okay. Yeah, it seems to be like pi by 2. Okay, let me do it. So I think if I find some contradiction, then I will come back. But so far what we observe is like from -1 to 0, 0 range of y. If I take sine inverse y, then I get ranges for x to be minus pi by 2 to 0. Okay, and for which we are computing this, right? So we have this PDF of x. Okay. And cos of sine inverse y, right? So this I can write this as what? So sine inverse y is x1, right? Okay. So one step would be minus like, yeah. So sine inverse of sorry, yeah. Square root of 1 minus sine square. Okay, let me do it in a one like. Okay, so what I can do is like 1 minus and then sine square of sine inverse y. Okay, so or I can write it compactly as sine square x1. Okay, so sine square x1 is y square, right? So this is like pi by 2, and then sine square x1 is 1 minus y square. Okay, this is what I get in this. Now now what I will do is like in now I will go for y in 0, 1. Okay, and if I go for y in 0, 1 range, then yeah. So if y in 0, 1 range, okay, let us continue. And this is fx x1 divided by g prime x1. So y in 0, 1 range, I think there is something I'm myself missing from the method of transform. Maybe I have missed something here because I think what we are supposed to do is to find the, like we have to also see the partition for the y range, and within the y range we have to see where it's monotone. Like for instance here, this is the y range, let us say, and this is where I found it monotone, right? And then from here to here, let us say this is another y range, right? And here I need to piecewise make it so here it will be in two parts. Okay, so I think what I am missing actually from the method of transform is I have to also look into the partition of y. So the partition of y is like, in this case is like -1 to 0. Okay, so this is the partition of y, and then union of let us say 0 and 1. Okay, so in this case, like, okay, so -1 to 0 I have figured out. Okay, so this is where I have written, and then for this part, and then I go back and see from here to here, like how I can split the range of x. Okay, so range of x is, so in this partition now I see the range of x is like 0 to pi by 2, and then union of pi by 2 to pi. Okay, now yeah, so yeah, so in 0 to for the y in 0, 1. Okay, so let us see for y in 0, 1 I have the two partitions here. So this is like x1 in for this case I have x1 which is this part and x2 which is this part. Okay, for which I will find the inverse. Okay, so this will be plus fx x2. This x1 is not the same as this x1. This x1 was this x1, right? Okay, so let us work through this and see if this makes sense. Okay, so g prime of x2. Okay, so this is what we have. Like this is on the partition 1 and this is on the partition 2. Okay, and this is for y in 0, 1. Okay, so okay, so now if we compute this, right? So if we compute this, then this will be what? Fx of sine inverse y by mod of cos of sine inverse y. So that's what we know. And then other term will be similarly fx, and then so what will be like the inverse you define for the x2 part, right? So the x2 part is this, right? So if I have to write the inverse of this, then I can write this as pi minus of sine inverse y. Okay, it's like pi minus of sine inverse y. Okay, and then similarly, like here, like so, like it will be like cos of pi minus sine inverse of y. Okay, so so we have the two parts here. Okay, and now we have to do the usual computations we have, right? So this is like uniform of sine inverse y. Okay, so sine inverse y. Okay, so sine inverse y, what are the ranges it have? So it's the ranges of x are going from 0 to pi by 2, right? So ranges of x are going from 0 to pi by 2. And we have a cos of this. So this will be the same as before because this is like, yeah, so this will be same as like this. Okay, so here like we have to sine inverse minus y is 0 to pi by 2, right? So this will be uniform over pi by 2. So this will be like again pi by 2 square root of 1 minus y square plus, and this will be how much? So this would be how much? A PDF of pi minus sine inverse y. Okay, so here in this case, it's going from where? Pi by 2 to pi, right? So this will be again pi by 2. Okay, this will be like pi by 2 again. And then square root of 1 minus y squared. Okay, so this is the uniform over the ranges here, right? Okay. Okay. I hope there is no mistake I have done anywhere. So if we now combine, so we have separately done for y minus 1 to 0, and then we have done for y between 0 and 1. Okay, so if we combine these values, then what will be the summary? Okay, you should do this also, double check this again. Okay, so here, so it was pi by 2 square root of 1 minus y square in this range. So pi by 2 square root of 1 minus y square when y was between 0 and minus 1 and 0. And here it was pi, I think, yeah, just pi. Okay, so pi by square root of 1 minus y square. And this is for 0 less than y less than 1. Okay, this is what. And then otherwise it will be 0. Okay, so we believe that we have done it in a good way. Okay, I don't see any. Yeah, so we have so how did we go about this? We divided the range into two parts, and within the range we have seen wherever wherever the function was increasing or decreasing. So in this case, like from here to here, we break the y, and then we found that it's increasing from the 0 to 1. We found that there are two parts of x where one part is increasing and one part is decreasing, and then and then for the one part we have like between 0 and minus 1 and 0 we found so we have this, so PDF of x1 divided by this, and then this is like PDF of x1 is sine inverse y. So we have done sine inverse y, and then we find that the sine inverse y range is between on the left side it between like minus pi by 2 to 0, right? So from there we compute the uniform. Okay, and then we have this, and then for 0 to 1 we found that there are two parts. Okay, and then for the 2 parts, we have the ranges from 0 to pi by 2 and then pi by 2 to pi. Okay, so this is what we have, and then we added this piecewise terms, and once we have this, then we combine these terms and then we write this summary. Okay, so one thing to check would be, so check this, okay, as an exercise, check that this is valid PDF. It has to be valid PDF. For this to be a valid PDF, okay, so you have to verify. So minus infinity to infinity, y must turn out to be 1. Okay, so this is a check we should always do to check for errors. Okay, so like I will also try to do this check offline to make sure that what I have done is correct. Okay, okay, so we have similar distributions like we had in the discrete case. So let us say in the continuous case, also we have uniform distribution, and we have seen this before. Like so the expectation of the uniform distribution will be given by x and then times the PDF, and if you compute this, then this will be a plus b by 2 CEG. And to find the variance, we have to do first compute expectation of x square, and if you compute this, these are easy things to do, and then the variance will be expectation of x square minus expectation of x whole square. So using these 2 terms, you can compute the variance of x now. So this for formality, like mean and variance of a random variable, of a uniform random variable. And we have something called exponential distribution. Okay, so and these distributions are defined by some formula, like, okay, so you may feel like why someone is doing this, but there are reasons. When we do problems, then we see the reasons. Okay, explicit reasons why we consider this, but the way it's defined, it will look abstract for you, like why things are like this. Okay, but it is like this. So lambda is greater than 0. So this x is the exponential if it satisfies this if it is defined by this PDF. Okay, so that's how exponential is. You have to memorize this. Okay, and the PDF plot will be like this. Okay, so for various values of lambda. So this is exponential. So this is how it looks like. So this height lambda will be this. Okay, at 0. Okay, and the CDF will be given by 0 to x. In general, the CDF was defined to be like this, minus infinity to x, but then minus infinity to 0, the function is anyway 0, defined to be 0. So it's better to start from 0. So 0 to x. Okay, so this will be, in this case, it will boil down to 0 to x. So this will be lambda e to the minus lambda t dt. Okay, since we are using x as a limit, we should use some other variable in the PDF, which is t dt, right? So this will come out to be this. Okay, so I leave this up to you to verify this. Yeah, lambda will get cancelled because integration, right? After integration, this lambda will come down. So that's why you don't see any lambda factor anymore. So expectation, these are formalities. Okay, so expectation is like x times the PDF. So if we do this and then we do the calculations, it will come out to be this. Okay, so these integrations, like I leave it up to you. You are good with this type of integrations by now, so it should be okay. Okay, there some simple tricks I've done are substitutions like lambda x is y and so on. Okay, but these are the like just to like make it compact form and then so on. Okay, you can also integrate it directly. It doesn't matter in this case. Okay, but anyhow, like this integrations can be found. Okay. Okay, I think I have to stop here. Yeah, so we will continue with distributions in the next class, and do remember to check that sin x sin that example. Okay, I will also try to check just to make sure that we didn't miss anything while doing the calculations. Okay, so I think with this I will stop, and yeah, have a nice day, and the grades will be submitted in few minutes. Okay, thanks.